Hi, I'm Kavya,
And I'm Eric.
and we're presenting on our final project for CS249R, which is TinyFederated transfer learning. So first, just to set up the task of federated learning, it's a recent field and area in privacy-preserving ML that involves a learning scheme that has the ability to learn from a lot of different distributed devices without ever making the data leave the device. So this could either be due to privacy concerns, communication costs, or storage costs. And so this makes it really perfect for TinyML because we have a lot of small resource-constrained microcontrollers that are deployed in the field. And we might want to be gaining a lot of insights from these that were not possible before. And so just to really quickly go over what the current state of the art is in federated learning, it's an algorithm called federated averaging, where you have a bunch of different devices on the edge that train their own local models and then periodically average them with a global server and then get an average model redeployed back to them. And so this involves like the weight sharing without actually like sharing the data itself. Again, this is like this algorithm works really well in a lot of scenarios and it doesn't work well in other scenarios. But our focus is being able to deploy this federated averaging algorithm on Arduinos and microcontrollers in general.
In our work, we also combined federated learning with transfer learning, where we took two models, one trained on ImageNet and one trained on visual wake words, and made it learn how to identify cats versus no cats. Next, you'll see our results.
So just to go quickly through what some of our results were, we tested a lot of different things. We had an implementation that Eric is going to show later on in Arduino and in C++. But we also took the code that we had deployed on the Arduino and ran simulations with it. And so these next few slides are going to be results of those simulations. So first, just to talk about random versus pre-trained, the way that we had taken the model was we took one of these pre-trained models, which is essentially a feature extractor with a fully connected layer at the end, whose outputs then go into a softmax to get class probabilities. And so we removed those last layers and we're left with a feature extractor. So it'll take in an image of a specific size and then output an embedding of a certain size that kind of represents the insights that the network had gained. And we held this feature extractor as static. And so our goal in transfer learning was basically to learn weights on that final layer so that we could take a model that was trained on either the visual wake words task or the ImageNet task and move it into a different task, so like binary classification or a classification with a different number of classes than the original model was trained on, and a different, I guess, like classification task in general. And so what the first consideration here is like random versus pre-trained. So in transfer learning, you can either have that final fully connected layer as completely random weights to begin with, or you can have it as pre-trained on like a different data set. So in our case, we pre-trained on a different part of CFAR, which was dogs versus no dogs. So again, like our actual classification task is cats versus no cats, and that's what these graphs are on. And so you can see that there honestly isn't a significant difference between the validation accuracy of the random weights model and the pre-trained on dog versus no dog model. And so honestly, if anything, like the random weights had less variability. So this basically points to, and it's a pretty good result because it points to the ability for us to take this feature extractor, which was trained on something completely different, and have these features that are generalizable to a lot of different tasks. And so this means that you could dynamically decide to deploy the transfer learning on a device without having in advance to transfer weights over from some other pre-trained task. And then now I'm just going to go over a few different like hyperparameters that we look through. So the first is local episodes. So in federated learning, we have obviously like the weight averaging with that global model, but we also have like the local episodes that each local model is being trained for. And so we wanted to explore, like what are the effect of the number of local episodes on the training accuracy. And so we can see here, like 1 would be like the data only gets passed through once, and then 6 would be it gets passed through 6 times. And with more local episodes, obviously like the training accuracy is higher because the model essentially overfits the specific data. And generally that also means that there's less variability in the validation accuracy epoch to epoch, which is a good result. But I think the trade-off here is like the trade-off of like the computational cost and the burden of doing the extra like episodes of training. And so here you can kind of see between 5 and 6, there isn't a significant increase in validation accuracy. And so it seems like either 5 or 6 is a good number of local episodes for us to be able to train this task on. In terms of the number of devices, so this would be the number of devices participating in federated learning, where number 1 essentially means no federated learning is occurring, aka only one device has access to all the data. And so here, just to note, the x-axis is a training example seen across all devices. So in the federated learning examples, each device doesn't have access to all of these training examples, but rather like different devices have access to different parts of the training data. And so you can see here that as the number of devices increases, both the training and the validation accuracy decreases, which can be expected because there is a trade-off between privacy and performance, as we can see here. Some of these like model updates might cancel each other out and things like that. And so not every piece of data is like insights are getting put into the model. So yeah, that's our analysis on the number of devices. And then finally on batch size. So in increasing the batch size, just in general, we anticipate that there's less variability in the model just because it's seen more examples. But we can see again, like having a larger batch size obviously has a trade-off in the real world in terms of having to aggregate the data and not have instantaneous inferences and training. And this also creates a lot of problems for like asynchronous like model updates to central server and things like that. And so we can see here like the major finding for batch size is that with a smaller batch size, there's obviously like a lot more variability in the epoch to epoch like validation accuracy and a lot more overfitting in the training because there are fewer examples to be able to fit onto. But overall, like all batch sizes have like an upward trend. So this means that even a batch size of 1 has good results.
Great. Now that we've seen the results, let's quickly go to the demo. Where first you'll see on the middle of the screen, the Arduino is starting to capture from the ArduCam, which is a 5 megapixel camera. It kind of does inference on it and then trains. After it trains, it wants to communicate with the server, which is represented by the terminal on the left. And the server here is sending the Arduino the model updates to its weight and bias. And after updating the weights, the Arduino will retrain and send back the weights to the server. You can see here that it does take a while because the weights and bias are encoded as bytes and set in 32-bit packets through the serial monitor. So here you can see the server receiving the updated weights. Cool. So finally, a few results. So on performance on device, for our memory footprint, we deployed the MLPerf MobileNet trained model on visual wake words because it was a smaller model. And it took around 210 kilobytes of dynamic memory and 657 kilobytes of flash. And as you just saw in the demo, the inference time took a few more seconds because the ArduCam had to take in the input and then process it. And the training actually was super fast with 20 local epochs. It only took 214 milliseconds. And finally, the communication with the global server took 1 minute, which could be improved with a smarter encoding method or pruning or some other technique. Finally, in conclusion, we have a summary of our contributions. The first is implementation of the federated learning on a microcontroller, which is the first implementation that we know of. We also showed a method of deploying transfer learning on the microcontroller without having growing storage costs as the number of training examples increase. This is a direct result of using FL. We also demonstrated the efficacy of having one-shot examples, as Kaveh showed through the graphs earlier, and also that the pre-trained weights are a necessary kind of attribute for transfer learning. And this means that devices, edge devices can be retrained for different classification problems. We also identified challenges and limitations in our paper, which I encourage you to read. Thank you so much.